let's do some guided practice on continuity. Here, we're going to find where f is discontinuous, like which x values f is discontinuous, and we're going to classify the type of discontinuity. Now, there are 3 types of discontinuities we can have. The first is a hole, right? We have something like this. Maybe the function is defined, maybe not. It doesn't matter. We have a hole. The next type of discontinuity we could have is something called a jump discontinuity, right? Something like this, where the function jumps up or down. And then the last type of discontinuity we could have is an asymptote, right? Something like that. So let's just label these, right? This is a hole. This right here is a jump. And this right here is a vertical asymptote. All right, those are the 3 types of discontinuities we could have. Now, to make things a little more challenging than before in the lecture, we're not given any x values. We need to figure out where f is discontinuous. Well, remember fact 2 from the lecture, right? If we have functions that are continuous, then so are their sums, differences, multiplication by a scalar, products, and quotients, right? So what that means for us is that since x minus 2 and x squared plus 2x minus 8 are continuous, right? They're polynomials everywhere. Then so is f of x, except where x squared plus 2x minus 8 equals 0, right? Because then we will be dividing by 0. So let's take a look here. We have f of x. Well, so on the one hand, I guess we could just say, so let's see, just note, before we talk about f of x, let's just note that x squared plus 2x minus 8 can be factored into x plus 4 times x minus 2. So maybe I'll say, x squared plus 2x minus 8 equals 0 at x equals negative 4 and 2, right? So note that they do want us to sketch the graph, right? We're gonna find where it's discontinuous. I think we just did that. But then we want to sketch the graph, and maybe that'll help us classify the discontinuities, right? Right? So let's just point out that f of x equals x minus 2 all over x plus 4 times x minus 2. Right? Right, so maybe we could say, okay, f is discontinuous, or maybe I'll just say not continuous, right? Whatever, not continuous at x equals negative 4 and x equals 2. Right, now we can classify the discontinuities when we sketch the graph. Let's sketch the graph right now. Yeah, let's just keep the pattern consistent. Well, we need to, I guess, we need to draw it over here, I guess, don't we? We need to go here. All right, so let's say this is our negative 4. Maybe this is our 2. And so, not the easiest thing to graph this, except let's take a look. We can actually cancel those guys out, right? So really we just have 1 over x plus 4. Now, if you remember the graph of 1 over x, it looks something like this. And 1 over x plus 4 just shifts the graph to the left, right? So if you notice, right, 1 over x plus 4 is going to give us a vertical asymptote. Right, so our graph is going to look something like this. It'll just be a little more clear like that, right? And then it's going to be like this. And you might say, well, wait a minute, don't we have a vertical asymptote for x equals 2? Well, we actually don't, right? Because we had it in the numerator as well, so we could cancel it out. Now, that still means f is not defined at 2, right? It's not, right? But what it does mean is that we have a hole instead of an asymptote. So our graph actually looks something like this, right? So here we have a hole, and here we have, well, I hope you can see this one is an asymptote, right? So those are our two discontinuities. Asymptote, x equals -4 is an asymptote, and we have a hole at x equals 2. Let's take a look at this. Now, don't worry so much about this one because we didn't actually define the ln function. We will do that in section 3.6, but I'll just tell you that you're not allowed to have ln of 0. So I'll just say, note, ln of 0 does not exist. That's what you need to know for this problem. Oh, and we're going to go back to blue, by the way. All right, so note, ln of 0 does not exist. Let's just kind of separate this stuff here. Okay. Maybe I'll actually just say, also, ln is continuous where defined. Again, we don't need to know too much of this right now, but really what we need to know is that 3x plus 2 cannot equal 0, right? So x cannot equal -2/3. Okay? Or maybe x cannot equal -2/3, right? So I guess we could say, so f is not continuous at x equals -2/3. Now, another thing you need to know about the graph of ln is that at wherever the argument, like the input, equals 0, which in this case is -2/3, right? Whenever you would get 0, that's going to give you a vertical asymptote, right? So it turns out you have something like this. Right? And it turns out ln is also not defined for negative numbers either, unless you have absolute value signs. Right? So I think it's clear then, looking at the picture, that we have an asymptote. Okay? Maybe not last, but let's keep going, right? At this point, we have a piecewise function. This is something we need to deal with a little bit more, right? This is a bit more common. This is something we might see on a quiz or an exam. Not a quiz, we won't be quizzed on this, but an exam. Right, so let's see. We've got a piecewise function. Both pieces are continuous. So check only 0. Check only x equals 0. So the limit as x approaches 0 of f of x, well, not too sure, right? Because it's a piecewise function, right? Let's just jump to the left piece. That equals -7. Limit as x approaches 0 from the right of f of x. Oh, look at that. It also equals -7. It's also worth noting that the left-hand limit equals f of 0, right? Because it's defined, maybe I'll use a yellow for this one, right? It's defined at 0 to be that, right? So the limit as x approaches 0 of f of x equals -7, which equals f of 0. So f is continuous. Okay, so there are no discontinuities. I don't really want to draw the graph to confirm, but no, that's not true. I should do it, right? So 3x minus 7, we've got a line, right? The y-intercept is -7, something like that. And then at this point, we have x squared minus 7. It's a parabola. It's something like that, right? No discontinuities, right? Moving on, right? Let's see. We've got 3 more problems. Here we have another piecewise function, okay? again, f is continuous on both pieces because they're polynomials. So check only x equals -1. So we're just going to look at the limit as x approaches -1. And let's just jump to from the left. That's going to give us -4 plus 5, which is 1. Which, again, equals f of -1 because f is defined at -1 accordingly. Okay? And then the limit as x approaches -1 from the right of f of x is going to be this. And again, we just plug it in. See, notice that taking the limits in this case is not actually very hard, right? It's more just knowing what to do. So this is going to be 1 minus, plus 2 minus 6 equals -3, I guess. You see how these two limits do not equal each other? So, the limit as x approaches -1 of f of x does not exist. So f is not continuous or discontinuous at x equals -1. And then the question is, what kind of discontinuity is it? Well, let's try to draw the graph and see what we get. Well, 4x plus 5 before -1. So let's see, we know that at -1 we're getting 1. And I guess that is defined there, right? The hole is filled in. 4x plus 5 is very steep, so we have something like that. It's probably even steeper than that. But for illustrative purposes, I'll do that. Now this parabola, given that we're starting at down here at -3, we know it's an upward-facing parabola because this is positive, right? If it were downward-facing, then it'd be negative. So we'll have a hole there, and then we're just sort of going up like that. Maybe just a little like that, okay? So I hope we can see here that this is what kind of discontinuity? It's a jump discontinuity. Next, we have, a cube root. Nasty. Now, one thing to keep in mind is square roots don't work for negative numbers, right? Even roots don't work for negative numbers. Odd roots do. So the domain of f, the stuff you're allowed to plug in, actually is all real numbers. So let's just point out, since the cube root of x and 5x plus minus 9 are continuous, so is f. So f has no discontinuities. That was easy. Nice little break. Okay, well, I don't think we're going to get away with that with this one, right? Last one. Make it happen. So here we have a sort of double piecewise function, right? 3 pieces. So there are, 3 pieces, but actually there's only one value we really need to worry about, right? So again, since all pieces of f are continuous, right, because they're all polynomials, check only x equals 1, right? That's the only place where we could possibly have a discontinuity. So we just take a look at the left-hand limit. Limit as x approaches 1 from the left of f of x. Just plug it in. Let's look at the right-hand limit. Well, if we're looking at x greater than 1, then I hope you see that we're doing this function, right? Because that's what's defined for x greater than 1. And we plug it in. And we get negative 4 plus 2. Oh, it equals negative 2. So the limit as x approaches 1 of f of x does exist, and it equals negative 2. So f is continuous at 1, right? Yeah, if I ever ask a question like that, then that means the answer is no. But f of 1 equals 3, which does not equal the limit as x approaches 1 of f of x. Right? So please, please, please be careful about that. Even if the limit exists, that does not guarantee that you have a continuous function. So f is not continuous at x equals 1. Well, let's see why not. Let's see what kind of discontinuity this might be. Okay, it looks like we've got a problem at 1. So 2x squared minus 4, that's a parabola of sorts, a pretty steep parabola, but it's going like this. Let's see, at oh, I guess we need to be a little more careful here because we're talking about negative 2 here. So, right, if this is our x-axis, this is our y-axis, and we're sort of interested in this negative 2 value over here, well, I guess at 1, get out of here, we've got a hole here, right, where we've got this sort of steep parabola right before. Okay? And then afterwards, we have a downward sloped line, very steep line going like that. So weird behavior. But actually, as it turns out, our function is defined even lower. So we have something like that. So what kind of discontinuity is that? It's a hole.